remember that already last week we talked about games, but last week we just talked about games in general, and we also discussed this Lie calculus mechanism, which I claimed to be some piece of math that we can use to solve games, but actually we did not discuss how we can really solve games, so how can we compute strategies in a game to always win the game. And this will be the topic of today's lecture. So the motivation, the general, bigger picture is as follows. In this lecture, in this class, we would like to synthesize systems automatically from their specification, and in the first part of this lecture we will mostly focus on so-called reactive systems, which are basically like hardware systems, basically. We have as an input to all our algorithms a specification, and the final output should be an implementation of this specification, for instance in form of a hardware circuit. It could also be a Python program. Now, the important thing is that the specification only defines what our system should do, but not how. The synthesis algorithm will then come up with a solution of how this can work and how this can be implemented. In the first lecture, we talked about specifications. Georg told you about this linear temporal logic. Here I also wrote an example of a specification in kind of linear temporal logic. I just did not use these operators G and F that were introduced by Georg. I just wrote the name out to make it more readable. And Georg also told you about other ways to specify systems, for instance in form of Buechi automata. So this was the content of the first lecture. Now, last week we talked about games for solving the synthesis problem, and we said that the synthesis problem can be modeled as a game between two players. There is the system that we would like to construct, and we always look at the game from the perspective of the system. We are always the good guy playing this synthesis game from the perspective of the system, but there is also our opponent, the evil environment. And the synthesis game basically is played in the following way. There are rounds, and in every round the evil environment provides some inputs, then we have to respond with some outputs, then in the next time step the evil environment provides the next inputs, and so on, and this interaction is going on forever. Basically we have to react to inputs continuously. That's also why these kinds of systems are called reactive systems that we would like to construct here. The important point here is that, so these are the rules that we follow when playing the synthesis game, but we also have a winning condition. And the important point is that the winning condition for this game is defined in such a way that we, the system player, win the synthesis game if we manage to satisfy the specification. So winning the game means satisfying the specification. This means that we can compute a strategy to win the game, because a strategy to win the game is then also a strategy to satisfy the specification. So this is the crucial point how we can use games for solving the synthesis problem. Now, in the last lecture we looked at very specific kinds of games, which are games on graphs, and recall that these graphs look somehow like this. We have two different kinds of states. There are these box states, where our evil friend here gets to choose one of the successor states. And then we have the circle states, which look more like X here in this picture, but anyway, these are controlled by our system player, and here the system player gets to choose the next states. Intuitively, the choice of the evil environment player in such a box state always corresponds to picking one of the inputs. For this example specification here, R would be an input and G would be an output, so the specification would say, at any point in time, if the request input is set, then at some point in the future some grant output needs to be set. And this game actually matches exactly this specification here. So the choices done by the evil guy here correspond to different choices of the inputs, and the choices done by the system player correspond to different choices for the outputs. So we have these games, and last week we talked about Lie calculus and how to reason about these graph-based games. And in this lecture we will discuss how we can solve such kinds of games, and this will happen in 2 steps. First, we will compute a so-called winning region. The winning region is simply the set of all states in this game from which we can win this game. And then, as a second step, we will compute a winning strategy, and the winning strategy just tells us what we should do in which situation in order to win the game. Our choices are basically just always picking one of the outgoing edges for all these circle states. So a strategy just looks like this. We just pick one of the outgoing edges for every state, or at least one of the outgoing edges. We can also pick more if more leads to winning the game. But after this lecture, we will still not be done with our complete synthesis flow. Next week, you will learn what you should do once you have such a strategy, namely how to turn this strategy into some implementation, for instance, a circuit which implements the strategy. So this will be then the content of next week. The outline for today is very simple. Before we start, we will review a few definitions and terminology. This will mostly be also a repetition from what we already discussed last week. And then we will look at 4 different kinds of games: reachability, safety, Buechi, and generalized Buechi game. And we will see how we can compute, first of all, a winning region in these different kinds of games, and second, a winning strategy for these different kinds of games. The learning targets is that you should know what these different kinds of games are, and you should be able to compute a winning region by hand. We will also do this on the blackboard in the class. For this, you will have to understand the corresponding Mu calculus formulas and know how to evaluate them. And finally, you should also be able to compute a winning strategy for these games by hand. So let's start with some definitions, which is mostly a repetition of what we already discussed last week. So remember that the games that we are dealing with here are games on graphs, and they are defined by 2 components. First of all, a graph, and second, a winning condition on this graph. The graph is quite a standard graph. It has a certain set of states. It has one special initial state, which is called Q0 here. The special thing is that the states of this graph are divided into 2 different kinds of states. There are these box states here, which are basically they are the circle states, first of all, which are part of this subset Q0, and these states are where player 0, this is our system player, our good player, this is always us, picks a successor state. And then we have the box states. This is where the evil environment player, player 1, picks a successor state. So a game this game is played as follows. We always start in the initial state. Let's say I'm the evil player. This is a box state, so I can choose a successor state. I can choose to go to Q3. Q3 is again a box state, so I can choose again, and I can choose to go to Q1, for instance. Now Q1 is a circle state, so this state belongs to you, to the system. So you can choose either to go to Q2 or to Q5. And this choosing of successor states is repeated in an infinite execution. So a play of this game is always an infinite sequence of states. So much for the game graph. The winning condition, formally defined, we could say it's a function which takes as an argument an infinite sequence of states. This is usually written by q to the power of omega. This omega always means something infinitely large. But what this winning condition basically means is it takes as argument a play, so an infinite sequence of states, and it returns either true or false. Namely, it returns true whenever the system player, you, win the game, and it returns false whenever the evil environment player wins the game, which is me in this case. In practice, we will encounter different kinds of winning conditions which are not defined in such a complicated way, but often defined in a much simpler way. Typically, the winning condition on our graphs will be defined by a certain subsets of the states. For instance, a typical winning condition could be to reach a certain state at least once, or to stay in a certain set of states forever, never leave it. or to reach a certain set of states not only once, but infinitely often. And usually we also name the game according to the winning condition. So when we have a game with the winning condition of reaching a certain set of states, then we call this game a reachability game. If we want to stay in a certain set of safe states forever, then this is called a safety game typically. And if we would like to reach some set of states infinitely often, then this is called a Buechi game, similar to the Buechi automata that you have learned about in the first lecture, where we also had to visit certain states infinitely often. Okay, so this is how our game is defined. Now, about strategies and winning strategies. In the most general case, we can define a strategy for the system player also as a function, and this function takes a finite sequence of states as an input. With q to the power of star, we always denote sequences of states that are finite, so this is the set of all sequences of states that are finite. But the sequence of states that we have as an argument for our strategy ends with a state that belongs to player 0. So where player 0, the system, needs to choose one of the successor states. And our strategy function just returns the concrete successor states that we should choose in this situation. So intuitively, this function takes basically the history of the play so far, so the sequence of states that we have seen so far, and this sequence of states ends in a state where we have to pick a successor, and now this strategy function just tells us which successor we should pick in this situation. So this is a very general definition of a strategy. In our lecture, we will mostly deal with strategies that are much more simple. We will call them positional strategies or memory-less strategies. These strategies are functions that look in the following way. Just for every player 0 state where we have to pick a successor, this function just returns the successor that we pick. So in contrast to this upper definition here, the general notion of a strategy allows the strategy to look at the entire history of the play so far. These special strategies, they are basically memoryless. They do not remember anything about the play so far. They base their decision which state to pick next just on the current state in which we are currently. And luckily in this lecture we will mostly deal with these positional strategies. We will not need this more powerful definition of a strategy. Now we can say that positional strategy for player 0 is winning for player 0 if intuitively this strategy makes sure that we always win the game, no matter how the other evil guy moves. So more formally we could say that a certain play follows a positional strategy if whenever this play is in a state that belongs to player 0, then the next state is chosen by the strategy by applying the strategy to the current state in which we are. This is just a very complicated way of writing down what you intuitively already know anyway how this works. So this is how we can formally define when a play follows a positional strategy, and then we can say that a strategy is winning from a certain state if when we start in this state, we will always win the game when we follow our strategy, no matter how the other player moves. One more definition before we go on with the real content of today's lecture. A winning region for a game, or the winning region for a game, is always the set of all states from which the system player can win the game with some strategy. Here is a graphical illustration. Let's say this box here represents the set of all states in the game. This is usually written as Q. Now, the winning region is a subset of this set of states. And the meaning is that whenever we start our game in one of these green states here, then we have a strategy to always win the game, no matter how the evil guy behaves. outside of this winning region, we cannot hope to win the game, not even with the best strategy. Outside of this winning region, there is some behavior of the evil environment guy to prevent us from winning the game, to make us lose the game. So our algorithms for solving games will usually work in 2 steps. First, we will compute this winning strategy, and then we can already distinguish 2 different cases. The first case is we look at our initial state in the game, and if this initial state of the game is in the winning region, then this means that we can win the game from the initial state. So on a more higher abstraction level, this basically means that the synthesis problem that is modeled as a game is realizable. There is a solution and we can compute it. So in this case, we will just compute a winning strategy, which really wins the game from there, and then we will implement this winning strategy. The other case is when the initial state Q0 is outside of the winning region, then this basically means that we cannot win the game, not even with the best strategy. There is some environment behavior which can make us lose. So in this case, the synthesis problem that we are trying to solve is actually unrealizable. There is no solution. In this case, we will just abort and tell the user, look, your specification doesn't have a solution. It's impossible to realize this specification. Why can this happen? Well, the user can write extremely stupid things, right? The user can write, there is system, it has one output O, and the user writes in all time steps, O must be true, and in all time steps, O must be false. This is a specification, but no system can ever hope to implement this specification because it's actually contradicting. So in such a case, our synthesis tool will figure out that the initial state is outside of the winning region for this game. Actually, the winning region for this will be empty. There will be no state from which you can win this game. And our synthesis algorithm will say, this is unrealizable, go fix your specification. Okay, now let's discuss how we can really solve different kinds of games, and we will start with, I don't know if it's the simplest kind of game, but it's a simple game. It's a reachability game. In a reachability game, the winning condition is defined via a set of states F, which intuitively is kind of like a set of target states that we would like to reach at least once. So formally we can define our winning condition phi, which takes a play and returns true or false whether or not we win the game, as follows. We say that we win the game, so this phi evaluates to true if there exists some state qi in our play such that this state qi is part of this target region F. So if there is at least one state in our play that is part of F, then we have satisfied our goal. We just want to reach F once. That's enough. So here are a few examples. Again, this box here is supposed to represent the set of all states in the game, and this green region is our set of target states F that we would like to reach. This red line here is supposed to visualize our play, so our sequence of states that we execute. Remember that our plays are always infinite, so I try to visualize them as a lasso. So this is executed once and then this loop is repeated. So a question to you. What about this first situation here? Is this play won or lost by the system? According to this definition of reachability. Yes, won. We just need to visit F, and we definitely manage to do this because we are always in F. What about the second one? 1. Yes. We need to visit F. Here we actually visit F infinitely often, but so that's more than fine. What about the next one?
It's also 1.
Also 1, yes. We do not visit it infinitely often, but we actually start in F. We then leave it, but whatever we do after we have already reached F, everything is fine. We just need to reach f once. What about the last one? Lost, because we never reach f. Good. We also can define this winning condition in a different way by introducing a function oc, which gives us all states that occur at least once in this infinite sequence of states, which is our play. And then we can say the intersection between the states that occur in our play with f needs to be non-empty, which basically means that the set of states that occur in our play must have at least one state of f, so that we win the game. This is just an alternative definition to this one. Okay, so let's now see how we can solve these kinds of games, and this I would like to do actually on the blackboard together. So we will just develop or look at the problem, develop some intuitive concept which may work for this example, and then later we will try to generalize what we have learned and try to create an algorithm. Our example game graph looks like this. Actually, you do not have to copy this, you can also find the solution then in the slides. This is our game graph. Actually, it's the same game graph from last week. We always use the same game graph. And we interpret this game graph as a reachability game, and the target region, F, for this reachability game is the set of states which only consists of state Q2. So this is this state here, and I mark it with a heart. So this is the state that we would like to reach. Now, a brief reminder how these games on graphs are played. Remember that whenever we are in a circle state, then we as the system get to choose a successor. But whenever we are in a box state, then the evil environment can choose a successor. Now let's first discuss how we can compute the so-called winning region for this game. So the set of all states from which we can make sure that we win the game. When you look at this graph, can you spot maybe at least one state from which you can win this reachability game?
Q1.
Q1, yes. So actually, I would even start with a simpler case, namely Q2. If we start with Q2, then we can definitely make sure that we reach Q2 because we already start there. So this state will definitely be in our winning region. And as you said, this other state, Q1, is also in the winning region. Why actually?
Because we can choose where to go next, and we definitely choose Q2 next.
Exactly.
There is an edge between Q1 and Q2 then?
Exactly. There is one edge between Q1 and Q2. We are allowed to pick one of the outgoing edges, so whenever we are here, we can just pick this edge and then we reach our goal. So, what we already know is from these two states we can definitely win. From these two states we can reach this target region of states. Now, are there more states from which we can be sure that we can reach this target state Q2?
I
Yes.
think also Q3,
Why?
because the environment can choose either to go to Q2, which means that I can win, or to Q1. And when I'm in Q1, I can pick my next state, and then I can also go to Q2.
Perfect, yeah. So here actually the evil guy has a choice. But none of the choices for the evil guy are good for the evil guy, because all of the two choices, from all of the two choices we can win then later. So actually, whenever we end up in Q3, this is also perfectly fine for us, because from there we can also win. So let me enlarge this picture a little bit. So what we already know now is that from these three states we can win. Whenever we end up in one of these three states, then we know what to do in order to win the game. We can reach Q2. Any more states from which we can win?
In Q0 it's the same here. Because
Same here. Exactly. We also have two choices for the evil player, but from all of these successor states we can win, so it doesn't matter what the evil guy does here. If it goes here, then we will go there. If it goes here, then he can choose again between going here or there, and if he goes here, then we go there. So also Q0 is part of the winning region. Also from here we can win. So this is our next best guess of what the winning region could be. Any more states we should include in this winning region?
More or less we win all the time because we have to start at Q0.
Yes. But actually the way we usually solve these games is we completely ignore the initial state. We compute the winning region, and once we have the winning region, we just check whether the initial state is in there or not. Now you are right. Once we have the winning region in our the initial state in our winning region, we can also stop. It doesn't really matter if we include more states or not. We can already stop, basically. So you're right. There are no more states from which we can win the game because let's take Q5. Q5 has some edge into the winning region, but we always assume that the evil guy is really evil, and this evil guy also has a second choice, namely going here. So in the worst case, the evil guy will just pick this edge, and then we are screwed. There is some chance that this evil guy does this move here, but we cannot really rely on it. From here we cannot enforce that we win. We would have to have luck, or we would have to rely on the stupidness of the other player. And of course also from here the evil guy can only go there, so the situation is the same. And from here we only have one choice, namely going there, but if this evil guy picks this edge here, then there are no more states from which we can win. So this, maybe I should do it in a different order. So this set of states here is our winning region for this reachability game. So the set of states from which we can win. Good. So this already gave us some intuition how these reachability games work. You can also find the same thing we just did manually here on the blackboard on the slides. Now, next I would like to develop an algorithm that computes the winning region a bit more systematically, basically. And in this algorithm, we will use an operator, which I call force here. Force takes as argument a set of states, which we call x. And intuitively, what it produces is also a set of states, namely the set of all states from which player 0, so us, can enforce that we reach a state of x in exactly one step. Let me illustrate this graphically. Basically, we have to distinguish two cases, which we already did in our example, right? Whenever we have a circle state, then it's sufficient if there exists one edge that leads to this target region x. If there is at least one of these edges, then this means that this state is part of force of x, because we can ensure from here that we reach x in the next step just by picking this edge. The other case is a bit more problematic. If a certain state is a box state, then the evil environment can pick a successor. So having one edge into the target region x is not enough. If there are other states, other outgoing edges that do not end up in x, then the evil guy could just pick these other edges, so we cannot enforce from such a situation that we end up in x in the next step. However, if the picture looks like this, as we had it, namely that all outgoing edges of this box state go into this target region x, then this means that from here we can enforce that we reach x in exactly one step. So in this case, this state would be part of force of x. In this case, it's not part of force of x. So we can formally define this force operator as follows, also just by distinguishing these two cases. Force of x contains all states, or Q0 states, for which it holds that there exists some edge from x, from this state q, to some state q prime, and this state q prime is part of x. This is just formally written down what is drawn here. There exists at least one edge from this state q to some successor state q prime, and this successor